to the Logic Colloquium. And our next speaker will be Matteo Viale from University of Torino, and he'll talk about strong forcing axioms and decryption.
Okay, thank you so much. So the talk is full of slides, but I guess that for most of you, many of those are really elementary, so I can go through very fast. And here is an outline of what we will discuss. So, well, there is, for those who have some familiarity with forcing axiom, well, the basic motivation comes from... do I...
Speak a bit louder.
Yes, yes. Is it active, this microphone?
No.
That microphone is just for recording.
Just for recording this one.
Okay, okay. I try to speak louder. Is it okay like this or no? Is this working?
Yeah, we switch on.
Check.
But I think we have the...
No, let's just... I'll try to speak louder. Apologies. Okay, so, well, this is one notion, one way we come to forcing axiom is by trying to reinforce as much as possible the Baire category theorem and to apply it to, I mean, the Baire category theorem says you want to, that for compact outer space, you can meet countably many dense open sets. And now you want to identify which class of topological spaces you can meet Aleph-1 many dense open sets. And then there is a, so what is the Baire category theorem? It's an existence theorem. You use it to find points that satisfy certain properties. So what you do, you say the property holds generically, it means it holds on a dense open set. And if I can meet countably many dense open sets, I can find a point that realizes simultaneously countably many properties. And the same type of approach to get a solution to certain mathematical problem comes from algebraic approach, which is to extend. So you have a certain mathematical structure and you have a certain problem in that structure that you cannot solve. And what you do, you adjoin a solution formally, and you maintain the basic properties of the structure. So, for example, you maintain that it is a ring in passing from Q to Qx mod x squared plus 1 equals 0. You maintain that the bigger structure is still a ring with not zero divisors and so on and so forth. But now you have a root of -1. A square root of -1. And the analogy in this case, I want to point out that this second approach is very much related to how one comes to bounded forcing axiom. What are bounded forcing axiom? They say that you have an existential statement which you can make true somewhere in the universe, in an outer universe, and then you reflect back the statement to the actual universe. And you will see why this is related. And okay, and then there is it's not that these two approaches, the geometric approach and the algebraic approach are completely unrelated. They are related. Usually those are the duality theorems. For example, the Hilbert-Nustellensatz says that if you look at the generic points of irreducible algebraic varieties, it's the same thing as looking at a solution of systems of Diophantine equations. Okay, so well, what is the relation? How do we transfer this in the context of forcing axiom? Well, essentially, we have theorems saying that forcing axiom, which are motivated by strengthening the Baire category theorem, are, let's say, well, in this case, we don't have a double implication, but we have at least an implication. So the geometric approach to find witnesses implies the algebraic approach to find witnesses. Okay, so star is a stronger type of bounded forcing axiom. Okay, and finally, I want to use a model theoretic tool, which is the notion of model companionship, to outline precisely these properties. So this relation between adding existential witness via algebraic approach or via geometric approach. And what I will outline is that in a certain sense, star is giving an algebraically maximal version of set theory, and determinacy axioms are also giving an algebraically maximal version of set theory. It all depends on the language you are interested in. So in the case of determinacy, you are interested in second order number theory. So you are looking at subsets of the real which are definable, and you want to maximize the number of consequences that are true for this structure. And in the case of bounded forcing axiom, you are looking at subset of power set of omega 1, and you want to maximize the number of consequences of this axiom. Okay, and well, this part maybe I can just rush through. I guess that everyone here is familiar with axiomatization of set theory. I use the axiomatization with Morse-Kelley. Why? Because I think the notion of proper class is a natural mathematical notion, so it should be included as part of the standard axiomatization of the concept of set. So what are the axioms? Well, you have axioms saying that when two objects are equal, that's the extensionality. Then you have comprehension, which says whatever property you can imagine, it's going to have to be a class. And then you have to say that every class is actually a subset of the universe of sets. And the proper classes are those subsets of the universe of sets which are not themselves sets. Okay, and then you have to say that you cannot, the epsilon relation is well-founded. And you can check that these are all universal statements, more or less. Okay, and then you have to say that certain objects are sets, because as of now we just have proper universal properties, but we don't have objects. So you say that empty set and natural numbers are sets. Those are objects. So natural numbers are given by God, and the rest is built by us, like Kronecker said. And then, well, this is the standard von Neumann construction of natural numbers. And then you have to say that if I have certain set and I apply simple operations, I still remain in the domain of sets. So if I have set X and set Y, I make the product, I maintain that it's a set. And if I have a set, I intersect with a property, I maintain that I have a set. Okay, and in this way I can build out of n, for example, I can build a product n cross n. So then I can build the integers using a property that separate that. Well, actually, n cross n. Well, it has to be careful, but I think already one can define the integers, then the rationals, and so on and so forth. With this stuff, already one can define all these objects. But if you want to define the reals, then you need more construction principle, you need the power set. And then in set theory, we also need the replacement. Well, the other mathematicians don't really need it, almost never, but in some occasions they do and they don't realize. And well, in some parts of mathematics, it's also important to have the axiom of choice. Okay. Okay, and then starting from this, one can define the notion of cardinality. And this is, well, I guess everybody knows. So you measure a set according to its size. So you say that two sets are equal if they are in bijection. And a set has smaller size than another if you can inject one into the other and or subject the other into the one. And you say that a set has strictly smaller size if you can inject one into the other, but not the converse. Okay, and then that's the first non-trivial result about cardinals. How do I get the pointer?
One above.
Yes. Okay, so this is, so you see this double relation says I have an injection from X to Y and I have an injection from Y to X, and it's absolutely non-trivial to say that from these two data you can cook up a bijection. So this is the first non-trivial result in cardinal arithmetic. So for example, it's easy to embed injectively and continuously the closed interval into the open interval, and conversely. But if you want to have a bijection between this object and this object, you have to go out of the continuous function. You have to go to the Borel functions. Okay, and that's also saying that the realm of cardinality is of infinite cardinality is non-trivial because X is always of smaller size than the power set of X. Okay, so one can climb up cardinalities and go to a very large infinities in this way. And then using replacement, you show that you don't stop at limit stages. You can continue after limit stages to build cardinals which are larger and larger. Okay, and also using the axiom of choice, one can show that this order relation on cardinals is a well order. So you have a very nice picture. So you start from 0, then you go to 1, 2, 3, 4, so on. Then you arrive at the first infinite cardinal, which is the natural number. And then there is a first cardinal, which is immediately bigger than the natural number. We call it omega 1. And then there is another cardinal, which is immediately bigger than omega 1. We call it omega 2. And, sorry. And then the continuum problem asks, is the power set of the natural number exactly the successor of the natural number in this hierarchy? Or, okay, so this, or if you want to say it without developing any theory of cardinality, if you have a subset of the real which is infinite, is it in bijection with the real number or in bijection with the natural number? And well, the point is that if you look at this definition, well, okay, then you start looking at the subset of the real and say, okay, which could be a counterexample to this statement? And well, you climb up in topological complexity and realize that, well, if you start with closed set or open set, you cannot violate this axiom. If you pass to Borel subset, also you cannot. And then even if you pass to analytic subset, so with analytic you get outside the realm of well, you may get outside the realm of measurability, but not outside the realm of counterexample to CH. Okay, so and well, I guess you all know what are analytic sets. So you start from a Borel set, you project, and you get analytic. The complement is called coanalytic or pi11, and analytic is sigma11. And then you continue to climb the hierarchy and to define the projective set. So given a pi1m set, you project, you get a sigma1m plus 1, and the complement is pi1m plus 1, and you go on and climb up. Okay, and then there is still a stronger notion of regularity, which is stronger than being projective. Okay, and you need large cardinals in order to infer that those sets are regular. Well, actually, no, you don't need large cardinal to assert that this class of sets are topologically regular, so they behave nicely. But you need large cardinals to assert that what you already know to be topologically simple is universally bare. Okay, and what is universally bare? Well, it says, okay, I'm a subset of the real such that whenever I take the preimage by a continuous function which has domain and nice topological space, what is nice, being compact Hausdorff, then I maintain that the preimage has the bare property in this space. Okay, and let's see if I have time. I think I can go because. So, and let's see why this is a nice topological property which is not so trivial. So, okay, so here is So consider 2 to the n as a closed subspace of 0, 1. It is a meager subset. Okay, now you take a subset of 2 to the n which does not have the Burke property. So you take, for example, you use the construction of using the axiom of choice that diagonalize through the sets with the Burke property. Okay, and now looking at it as a subset of 0, 1, you get that P is meager. So it has the Burke property as a subset of 0, 1. Okay, and you have a continuous map of 2 to the n into 0, 1, which is the inclusion. Okay, so you see that seen as a subset of 0, 1, P has the Burke property because it is meager. But when you take the preimage of this set by this continuous function, which is the inclusion of 2 to the n inside the 0, 1, you kill the fact that it had the Burke property. Okay, so you see this P, we expect it to be pathological because we build it using the axiom of choice in order to make it not have the Burke property. But inside this space, we cannot see that it is pathological because it is meager. But pulling it back using a continuous function, we get to a space where we can see that it is pathological. Okay, so this is one way to understand why this universal bareness is catching a notion of topological regularity. Because maybe in a certain space you don't see that it is pathological, but using the continuous function you can pull it back to other test spaces where you can check that it is pathological. Okay. And well, the great result of Steele and Martin is that universally Baire sets are determined. So if you have a game on 2 to the n where the payoff is a universally Baire set, there is a winning strategy. Okay, and this is a direct implication from large cardinals, and it is actually almost an equivalence because then you can build the inner models for exactly those large cardinals from this result. Okay, and then, well, what happens? That you have a game which where one of the two players has the winning strategy exactly if the payoff set has a perfect subset, and the other has a winning strategy exactly when the payoff set is countable. So this is saying that universally Baire set cannot give a counterexample to a continuum hypothesis, because if you take a universally Baire set, you play the game which decides whether you can embed a perfect set inside this universally Baire set, and either you can embed a perfect set into this universally Baire set, or the set is countable. Okay, and so you get that every universally Baire set is not a counterexample to CH in a very strong sense, in the sense that if it is uncountable, it contains a closed perfect set. Okay. However, CH does not follow from the axiom of set theory, so you can build a model where CH holds, and you can build a model where CH fails. And actually, if you look at what Cohen proved, he forced over L the counterexample to CH, and he produced a projective counterexample to CH. So actually, he had a set of size Aleph1 that was sigma 1, 2 in a model of 2 to the Aleph 0 equals Aleph2. Okay, so one way out, how do we solve this issue? So you see, CH is a very elementary question. I was able to state it in a few slides, and I guess that any mathematician with very little background understands the statement. So how can it be that it's impossible to solve it with our common mathematical axiom, accepted mathematical axiom? So Gödel had a program, and the idea is that we have not yet identified all the right axioms. Okay, because set theory is describing, he has a Platonistic sense, so set theory is describing a very precise mathematical reality, And in the axiom we have described some pieces of the properties of this mathematical reality, and probably we are missing some axioms to describe what is really true inside this universe of sets. And he also had a proposal for the axiom to be added, and he proposed that large cardinals should be added to the true axiom of set theory. Okay, and we have already seen that in retrospect, this idea of Gödel was full of motivation, because you had large cardinals, and suddenly you discover that the sets that should be simple, so for example the universally burst set, are actually simple because they are determined. Okay, and this is, I guess, one of the great achievements of these new axioms that at the time of Gödel were really exotic, but then in the last 60 years have gained a major prominence in set theory. Okay, and then he said, okay, not only large cardinals should be accepted as axioms, but then maybe we can find some other principle which to us it appears really exotic, but then we use this principle and suddenly a lot of problems which we are not able to solve, we find the solution, and it's the one that we expect, the natural solution that we expect. Then in this case, and then maybe after we found the solution, we can find another proof which does not use those axioms. Okay, so this means that those axioms are giving us hints of what is true, and so if they're really giving us so many hints that they are true, that their consequences are true, so maybe the axioms themselves should be regarded as true. And this is the success criterion. Okay, and then what are large cardinals? I guess that most of the audience know, but let me just say a few words. So the idea is that you want to be able to increase the height of the universe as much as you like, and replacement is giving you, replacement and power set are very powerful. From n you get to power set of n, power set of power set of n, power set of power set of n, and then at limit stage you collect all the power set you had using replacement, you take the union and you go on in cardinalities, but at a certain point you have to stop. You are not able to reach certain heights that instead large cardinal impose. Okay, and it appears that to some extent large cardinals are used also in other areas of mathematics, and they don't really care about the fact that they are using it. So for example, if one inspects the proof of Wiles of Fermat's last theorem, well, it uses the notion of Grothendieck universes, and in the way it is used in that proof, it really means that they are assuming the existence of inaccessible. Okay? Then, in retrospect, you can inspect the proof and realize that you can drop off the inaccessibility assumption. But the proof, as it is written in Wiles' proof, he is using inaccessibility, because he's using these Grothendieck universes, and when you think what they really are, the Grothendieck universe are just V kappa for kappa inaccessible. Okay, and if you want to do this algebraic geometry using these Grothendieck universes, typically you don't need just one Grothendieck universe. You have to make the Grothendieck universe out of Grothendieck universes. So you have to have another inaccessible above the one that gave you the first Grothendieck universe. And maybe you need another one because you want to do this operation twice or thrice. And if you do it, I mean, the neatest way is to say you have a proper class of inaccessible. In this theory, then the theory of Grothendieck universe is polished. Otherwise, it's a bit fuzzy if you have less than a proper class. Okay, and then there is another large cardinal that has received attention, at least outside of set theory, in particular in category theory, and it's Vopenka's principle. That's how the category theorists like to think about Vopenka's principle. So their way to say is I have a huge class of structure, and then it's not possible that these structures are all incompatible. So I have a huge class of structure, at least two of them must be comparable. So for example, in the case of directed, so in this case we take very elementary structures, so directed graphs with no loops, and the statement is, if I have a proper class of directed graph with no loops, then at least two members of this class must be comparable. I must be able to embed one into the other via, well, embed, to have one into the other via an homomorphism. Okay. Okay, and these are applications outside of set theory of this axiom. Okay. So you see in homotopy theory and yes, homotopy theory. Okay, so let's go to forcing axiom. Are there questions? Is it fine so far? Yes?
Maybe back in universally direct extension.
Yes.
So you have this property. You have this proper class of modules.
Yes.
If you don't have proper class,
Yes.
just a lot of them,
Yes.
you get the yield for a bounded amount of universal sets.
I think you have to.
What is bounded? I mean, so the representation, for example, like the small ordinal.
Is it fine the tone of voice, or do you hear?
Hardly. I need one four.
I'm
I'm
sorry.
happy with 1/4.
We'll talk later.
Huh?
We will figure out later.
Okay. Okay, so what are forcing axioms? Well, the idea is relative to a cardinal kappa. The forcing axiom states that you want to blow the power set of kappa and make it as big as possible. So you want to have inside this power set of kappa as many sets as it is conceivable to have. And how do you do this? Well, you have two ways. One is topological maximalities. So typically what you can do, you can look at power set of kappa as a compact Hausdorff space. It's 2 to the kappa, which is compact Hausdorff. And you want to find inside this space many generic points, let's say. Okay, so you want points that can simultaneously realize many open conditions. That's the topological approach, and it leads to Martin's maximum. And then you might have another approach. So you look at power set of kappa as an algebraic structure. So for example, you look at power set of n as the natural structure where to study second order arithmetic. Okay, so it's an algebraic structure, a first order structure, and you have many natural set theoretic operations for this structure that given certain subsets allow you to produce other subsets, and you want that your power set of kappa is closed as much as possible with respect to this natural set theoretic operation. Okay, so in this case the idea is really like the comparison between rational and complex number. So you have the rational. You have this equation, x squared plus 1 equals 0. You would very much like to have a solution. Well, if you just look at the rational, you cannot. So you go to the complex. You go to the complex. And here you have. Okay, so maybe you start with the model of set theory like L, where you have a certain subset of omega 1. From those, in principle, you can define others that are too complicated to be found inside L, but it's not inconceivable that they exist. For example, you can find them in a forcing extension of L. And then the idea is, okay, if it's not inconceivable that they exist, they actually exist. Okay, and so it's like we join the solution of square root of -1 to the numbers, and we maintain that we still can have a field where this solution exists. So we add to a model of set theory certain sets, and we still maintain that it is a model of the axiom of set theory. So this is the algebraic approach to maximality. Okay, and the rest of this talk is mainly aimed at formulating properly these two properties and to connect them. Okay, and those are let's say this is the strongest axiom of this type, and this is the strongest axiom of this type for the power set of omega 1. And then this is essentially the strongest axiom of topological type for Aleph 0, and well, to some extent, due to the nice theory of L of R that you get assuming large cardinals gives algebraic forcing axiom for Aleph 0. So they give a very neat and theory of power set of Aleph 0, and in this power set you are finding witnesses for almost all nice topological properties that deals with definable properties of the reals. Okay, so what is Berg category theorem? I already said you have a compact Hausdorff space, you have countably many dense open set, you want the intersection to be dense. Okay, and it's very easy to generalize the statement. So you replace natural number with a cardinal kappa, and you ask the same question. So if I have a family of size kappa of open dense set and I intersect them, do I get a dense set or not? Okay. And well, the point is that in general, this theorem is false. In the category of a compact Hausdorff space, this theorem is false. There are counterexamples. So you can cook up a compact Hausdorff space such that there are Aleph 1 many dense sets in this compact Hausdorff space, and you intersect them and you get empty set. Okay, so you have to go outside of, well, you have to restrict inside the compact Hausdorff space and identify what is the class of spaces for which this property can be true. Okay, and here comes a property of, well, the contribution of Abraham. He isolated a certain condition, which is, I mean, not so trivial. You already need to develop a certain amount of set theory to understand this condition, stationary set preserving. And if you have a compact Hausdorff space which does not satisfy this condition, then you know that this form of Berg category theorem for Aleph 1 many dense open sets is false. Okay, so when this condition fails, this axiom is false. Okay, so you get a necessary condition for this axiom to be true. Okay, the point is this condition also sufficient? So do we have that this is the case exactly and only when this condition holds? Okay, the fact that this is necessary is independent. So Martin's maximum is saying, yes, this is really characterizing it is an equivalent formulation of this property. Okay, so this is a picture. So you have this property SSP, which is in rows. Okay, then you have spaces that satisfies the forcing axiom, which is in the spaces which satisfy the forcing axiom are in rows. The spaces which satisfy the condition SSP are in orange, and the spaces which do not satisfy the forcing axiom for Aleph 1 many dense sets are in green. And you know that this part in rows is always included in this part in orange, but you don't know if they are exactly the same. And but you know that if you get outside of the orange part, certainly you are outside of those spaces that can satisfy this strong form of Berg category theorem. And Martin Maximum says this is the situation that you get. So you have maximized the quantity of topological spaces that can satisfy the strong form of Berg category theorem. Okay, so it's maximal in this sense. If this condition is failing, you are certainly not satisfying the strong form of Berg category theorem. But if this condition is holding, then you are satisfying the strong form of Berg category theorem. So you have exactly pinned the class of topological spaces for which it is not inconceivable that whenever you take Aleph 1 many dense open set, the intersection is non-empty. Okay, and the main contribution about this axiom is that it is consistent. So if, for example, given any large cardinal assumption, provided you have a supercompact cardinal around, then you can force that large cardinal assumption together with MM. So you see this can be put on top of the large cardinals. The large cardinals are already, let's say, accepted axiom of set theory. And if you want, you can add this MM on top of them, and there's no problem. Okay, and then there is MM++, which is a natural technical strengthening of MM, and I'm not going to discuss it here. And actually, you get the consistency of this stronger form of Martin's maximum by exactly the same proof. That proof gives this a model of this axiom. Okay, and this axiom has a lot of consequences. So, for example, it decides the size of the continuum to be the second uncountable cardinal. It decides also problem outside of set theory. So, for example, that Whitehead's conjecture on free groups is false. It decides questions about linear orders. It decides questions in functional analysis. Okay? And actually, all these questions are independent of this, even of set theory with large cardinals. So you have set theory with large cardinals, and you can cook up models where all these results have opposite answers. Okay, are there questions so far? I continue. Is it okay? Okay, then let me skip this part. Well, what is forcing? Well, here it's really not makes sense. Okay, so let me just mention that actually one can say that Grothendieck knew forcing, even if he was not aware of that, because when he developed this theory of Grothendieck toposes, well, actually part of his theory was a presentation of forcing in his own language. Well, and let me skip this part, but for those interested, I can come back eventually later. Okay, and now let's come to the, let's say, part which is less known even to set theorists. So why bounded forcing axiom are axiom of algebraic maximality? And why also large cardinals are axiom of algebraic maximality? And for this, we need the notion of model companionship. This is a notion in model theory, and it is meant to capture the algebraically closed structure. Okay, so let's start from the basic example, which is motivating even the notion of model companionship. So we have a notion of semi-ring, and you see the axiom of semi-ring in the natural language for this axiom is a all universal axiom. Okay, so you have a universal theory and you have a natural intended model for the theory. So for example, the natural intended model of this axiom is the natural number. Okay, then you realize that inside this structure you have certain operation which you would like to do, but you are not able. So for example, you would like to make subtraction, but you cannot subtract 5 to 3 because you get outside of the natural number. So you enlarge the theory and you go to a bigger structure where now you can make subtraction freely. How you do that? You do that by a pi2 axiom that says, well, now I can subtract and there's no problem. I stay inside my structure. Okay, and then you realize, okay, I also want to multiply freely, and here I cannot, because if I want to have fractions inside Z, I cannot have fraction, but there's no problem. I say, okay, well, I will have fractions. I go to Q, and how do I make it? Well, I say for every number, I can, provided that my number is non-zero, then I can divide it by 1 and then still have a number. Okay, and you see this is again a pi2 sentence that says for every number I can divide it by 1, provided it's not 0. Okay, and it's saying, okay, I had an operation for which I wanted the output to exist. It didn't exist in this structure, so I just enlarged my structure so that now the operation can be performed without problems. And then you have still a problem because you don't have algebraic roots of polynomial. And what you do, well, you add them formally, and you go from Q to the, well, actually, if you do this closure operation over Q, you get to the algebraic numbers. But what is that? It's formally, again, a family of pi2 sentences, which say I have a polynomial in a coefficient x0, xn of degree n, and I add a root of this polynomial. Okay, and you see again it is pi2 sentence. So what this is saying, okay, you start from a universal theory, and maybe in the standard model of this theory you see that there are certain problems for which you would like to have a solution, but you cannot have inside this model. But you can enlarge your model, maintain the truth of all these universal axioms, and find the solution of the operations that you could not perform in the former structure. Okay, and this is bringing to the notion of existentially closed structure for theory. So look at these three structures, so Z, complex, and a polynomial in complex variable. And now look at these questions. So the first question is, does x squared minus 2 equals 0 as a solution? Well, you see the question can be asked here. It can be answered positively here, but the solution you find here cannot be reflected here. And now you ask the same question. Does this polynomial x cubed plus 2x plus y equals 0 as a solution? The question can be asked here. You can check that there is a solution here, but actually you didn't have to go that far to find it. You found it right away here. You reflect the solution. Maybe you built it here because it was simpler. Here you have much more numbers to check, to look for your solution, but then you realize that it was stupid to go here to look for it. You could have just stayed where you were and you have it. Okay, and given a vocabulary tau, you have the notion of substructure for that vocabulary, and now you have the notion of sigma 1 substructure. Well, for logician this is trivial, so you want that quantifier free formulas which are true, for which there is a witness here, you can find the witness here. And well, there is a motivating, the example of numbers is coming, I mean, is motivating from algebraic geometry. So if you look at what are the quantifier free formula in this language over a ring, you realize that those are a Boolean combination of polynomial equation and polynomial inequation. Okay, so those are exactly the constructible sets of algebraic geometry. And the sigma 1 formula are saying a certain constructible set has a point. Okay, and depending where you are evaluating this constructible set, maybe in Q you don't find a point for this constructible set, but you go to the algebraically closed field and you find a point for the constructible set. Okay, so what are the sigma 1 formula? Are the existential quantification of quantifier free formula, and what now you have a theory in a certain vocabulary. So this is a first order theory in the first order signature tau, and what is you have a model of the in this, well, you have a structure in this vocabulary, and you ask when is this structure existentially closed? Well, first of all, I must be a substructure of some model of this theory S, and secondly, I must reflect all sigma 1 properties that I can make true in the bigger model when the parameters are coming from the smaller model. Okay, so I can reflect the sigma 1 property. Okay, and if you look at the theory of semi-rings with zero divisors, so that's, well, let's say semi-integral domains, or then you can pass to the theory of integral domains, which is rings with not zero divisors. Well, for this theory S, what are the S existentially closed models? Well, they are exactly the algebraically closed fields. And so this notion of existentially closed model is really capturing the idea that you're reaching a structure which is maximally closed with respect to the algebraic operation that you are interested in. Okay, so you see this is existentially closed for the theory of rings with not zero divisor. Okay, and now we have the notion of model companion. Okay, so what is, so you have a certain theory S, for example, the theory of integral domains, and you have another theory T in the same vocabulary, and you ask, is this theory T the model companion of S? What does that mean? Well, it means that this theory T is axiomatizing exactly the structures which are S existentially closed. So it is a way to say in a first order manner that if a structure realizes this theory T, it is really a nice structure, it is satisfying, it is having witnesses for all the simple problems that it is not inconsistent that they have a solution. Okay. Okay, and now so you see that now this is an abstract definition of what is algebraic maximality. So you have a theory S, and now you say, okay, I want to find the maximal structure, the algebraically maximal structure relative to this theory S. Well, I looked for those structures which are existentially closed, and I looked for the first order theory which axiomatize this class of structure. In principle, the problem is that in principle you might have a sensible notion of what is the class of structure which are S existentially closed, but it is not at all clear that this class of structure is first order axiomatizable. Okay, so having a model companionship result is very much dependent on the properties of S. So you could have theories S for which you have a nice notion of, well, you certainly know what are the S existentially closed models, but those models may not be first order axiomatizable. In this case, the theory S does not have a model companion. Okay, I move on. Okay, and the point is that now this notion of model companion can be applied to whatever mathematical theory, not just to the theory of algebraic numbers or whatever, but to whatever mathematical theory, provided you can give a first order axiomatization of it. And for example, you can axiomatize group theory. Well, what I want to point out here is that you have natural axiomatization of group theory and unnatural axiomatization of group theory. If you are teaching the first order course in algebra, you are not going to present the students this axiomatization of group theory. Okay, you are going to talk to them of this axiomatization of group theory. And well, those two axiomatization are equivalent. Well, you have to explain what is the meaning of this ternary relation symbol. Well, this ternary relation symbol means X times Y is Z. Okay, and now I want to come to set theory. And I think that the problem of us set theorists is that we didn't pay attention to the axiomatization. So we axiomatize our theory in this vocabulary, epsilon. Eventually, for convenience, usually textbook also have the symbol of inclusion, but in the official axiomatization of set theory, inclusion is a defined symbol, it's not part of the vocabulary. But there is a problem with this axiomatization. So for example, you have the notion of order pair, which is a very elementary notion. So it is not a doubtful concept. What is an order pair with first component Y and second component Z? And we have a standard trick to axiomatize this concept in set theory. So the order pair with first component Y and second component Z is the set with two elements. The first is the singleton of Y and the second is the pair YZ. And if you write down in the language of set theory, the formula saying that X is the order pair with first component Y and second component Z, you end up with this formula. And it is awful from the point of view of readability. It's also awful from the point of view of logical complexity. This is a sigma 2 formula. Okay, so you are using two alternation of quantifier to say that an object is an ordered pair. This is not a smart idea. So what you have to do, you have to add predicates and function symbols to talk about the elementary set theoretic concepts. And now there is a delicate point. What are the elementary set theoretic concepts? But this has been solved long ago. The elementary set theoretic concepts are the delta zero properties, and the elementary set theoretic operations are the functions which probably have a graph which is delta zero. Okay, so this is going to be our language. So the language I'm going to use is epsilon delta zero. So you have now constant symbol for empty set and the natural number. You have a relation symbol phi, which interprets the extension of a delta zero formula phi. And you have function symbols for a certain, well, let's say a finite amount of functions whose graph is described by a delta zero operation, by a delta zero formula. So for example, the function that given two sets give as output the product has a delta zero graph. So you put it among the functions in the language. Okay, and now you can formalize set theory, and you realize that most axioms in this new formalization are really getting the complexity you would like. So for example, extensionality is a pi1 axiom. Comprehension is a pi1 axiom. Foundation is a pi1 axiom. The existence axiom are, well, this is an atomic formula, and also this is an atomic formula, because you see all quantify. Well, actually, yeah, it is an atomic formula. No, maybe it's phi1. Okay, and then you see the basic construction principle that tells you that you can build, you can make the pair, you can make the subsets, and so on and so forth, are still pi1. And then you have the strong contraction principle, and then you are getting outside of the realm of pi1. So for example, comprehension that says for every property, you have the extension of that property. It's a pi2 statement. Replacement is well, it's actually pi1. And power set, well, this is the worst. Actually, if you unfold the definition, this is pi3. So you are not able to simplify too much power set. And that's why this is the problematic axiom. When you study the models of set theory, all the other axioms are easy to check, and power set is the more delicate one, and the one that is less absolute between these different models of set theory, because the definition is very complicated. It's a pi3 axiom. And choice is pi2. It says for every function whose range is given by non-empty set, I can find there exists a selector. Okay, and what is algebraic maximality for set theory? Well, I'm running. Okay, so you have to develop the theory of the H kappa. So I guess you are familiar with this. Does all of you know what are the H kappas? Well, okay, so the point is a set which has just one element is not simple. For example, singleton of R is not simple. To know this object, you must know R, and R is a very complicated object. So what are the simplest objects? The ones that are finite, all the elements are finite, and all the elements of the elements are finite, and you end up taking the transitive closure of the set, and you get that this is finite. This is hereditarily finite. Then you can do this for all cardinalities. And you do it with countable, and you end up with H Aleph 1. So a set is hereditarily countable if it is countable, or its elements are countable, and so on and so forth. And then you do it with Aleph 1, and you end up with H Aleph 2. And you can check that, for example, the singleton of real is not in H Aleph 1, because reals are not countables. Okay? Okay, I have to skip here. So, and here is the first indication that these H kappa are giving us glimpses of algebraic closure. So you take a formula with parameters in H kappa, sigma 1 formula, you find the witness in the universe, you reflect it back. It's true in H kappa plus. Okay, so this is an indication that this H kappa plus is an existentially closed structure. This is another indication that H aleph 1 is quite existentially closed. So you have a sigma 1 formula with real parameters. You find the witness in a forcing extension, you reflect the formula. Okay, and even if you have you can add the predicates for the universal Hilbert set. If you have a formula, you find the witness in the universe. And now you are allowed to talk about universal Hilbert sets, and the witness is reflected back to the ground model. Okay, and actually this is what you end up proving, that if you look at the theory of this structure in this language, well, this is the model companion of the theory of any forcing extension of the universe. So you see this structure is realizing algebraic maximality for set theory relative to a language which talk about universal Hilbert sets, so about the nicely definable subsets of the reals. Okay, so this is the situation. If you just have the axiom of set theory, you get that these are glimpses of generic absoluteness because it's sigma 1 elementary in the generic extension. But if you have large cardinal axiom, you actually know that this theory is the model companion of this theory. So you have a much better understanding of why this is the algebraically maximal extension of okay, and now you can do the same for the H aleph 2, and I rush a bit. So now the key predicate is the non-stationary ideal, and you have a notion of bounded forcing axiom, strongly bounded forcing axiom. So you consider just the forcing notion that preserves the meaning of this non-stationary ideal. And you want to reflect back the properties that you are able to force in the universe to H aleph 2. Okay, this is strong bounded for Martin's maximum. And it actually follows from MM++. And then it has many consequences. So for example, continuum is decided and Whitehead's conjecture is decided. And then you can also plug in the universal Hilbert set, and you have this notion of universal Hilbert bounded Martin's maximum plus plus. So you now can talk about non-stationary ideal, about universal Hilbert set. You look for an existential sentence in this language. You look for a witness in the generic extension which maintains the meaning of non-stationarity. If you find it here, you can reflect it back. This is UBPMM++. And it is again a consequence of MM++. And that's the main result of Asper and Schindler, that a certain other bounded forcing axiom, very complicated to state, which is called star, is actually equivalent to this UBPMM++. Okay. And this is the original formulation of star is considering not all universal Hilbert sets, but those that are given by the definable sets in L of R. Okay, and let me just say what happens with CH. Well, look at this pi2 sentence. This pi2 sentence in the signature where you have a predicate for aleph 1, sorry, a constant for aleph 1, you say f is a function, the domain of f is aleph 1. Well, then there is a real which is outside the range of S. F. This is a pi2 sentence, and is stating that CH is false. And the parameter you need to formulate this sentence in H aleph 2. And now you have this maximality result about star, which says that if you have a pi2 sentence that you are able to make true in some forcing extension, then it's true in the model of forcing obtained by UBPMM++. Okay, and actually you can reformulate this now just appealing to model companionship notion. So, and this is the result I want to point out. So this forcing axiom can also be stated in a poorly modeled theoretic terms as the statement that the theory of this structure is the model companion of the theory of this structure. So this is a model theoretic statement, and this statement exactly holds if and only if in the universe this axiom is holding true. Okay, and you get really a form of maximality, because it says that whatever pi2 sentence you are able to make true with the universal fragment of set theory in the axiomatization, it will be true in HLF2 of a model of BMM++. So, and this is the picture one gets. So from MK, you get that HLF2 is a substructure of its extension where the meaning of NS is preserved. From MK plus forcing axiom, you get that HLF2 is sigma 1 elementary in the generic extension where you are maintaining the meaning of the non-station ideal. If you plug in a large cardinal axiom, you get that the theory of all generic extension with respect to this language has a model companion, but you don't know what this model companion is. And if you assume that that forcing axiom holds in the universe, you get that the model companion is exactly given by the theory of HLF2 in the ground model. Okay, and I stop here. Apologies, I have gone over time.
Any questions?
So, like, this one is very big, but if you take H Aleph N with NS on kappa N's predicates, is there a known reason why this shouldn't be model companion to something? Okay,
the problem there is that we don't have the bounded forcing axiom, so we should have to prove a consistency statement first.
So maybe a deeper question, so like, is there something special about NS particularly on Aleph 1?
Well, yes, the point is for NS at Aleph 1, we can prove that it is saturated. It is consistent that it is saturated, and for all the other NS, it's a very difficult open problem whether it is consistent that it is saturated. And actually, in the proof of Asper and Schindler, this fact that you have a saturated ideal is very relevant in their argument.
I guess it's a continuation of the same question, but do you have a reasonable theory of H omega 3 in mind?
No, not at all. I mean, it's really not. Well, the point is that nobody, all the people that have looked at the theory of HLF3, they were interested with forcing axiom. They were interested at looking at forcing axioms that make the continuum Aleph3, and this is orthogonal to the setup studied here. So if one if one is accepting this idea of maximality, so now the theory of HLF2 is algebraically maximal, so one should look at the theory of HLF3 that preserves this property of being algebraically maximal for the theory of HLF2. So it means you should look at models where you have where you have this theory of HLF2, and this has not been looked at. I mean, the point is that Martin's maximum is already deciding a lot of stuff, so you are not going to have that much flexibility on what will happen at HLF3.
What do you mean by saying that determinacy is a form of maximality? What did you mean by saying that determinacy is a form of maximality?
I mean that large cardinals gives that the theory of HLF1 in that language. So let me get back. Sorry. So you see the theory of this structure, where you have the topological irregularity set as predicates and all the basic set theoretic concept as atomic formula. You have that this theory is the model companion of the theory of any forcing extension of B. Okay, so this is the sense in which it is algebraically maximal. And how do you solve a problem in this stuff? Well, typically you use the axiom of determinacy. Okay, so in this sense, I was saying that using the axiom of determinacy, many questions in second order number theory get an answer, and this is the powerful tool to solve the questions in second order number theory. And well, the fact is that this theory is catching the existentially closed models for the theory of sets in this signature.
Okay, let's thank the speaker again. So, going to the Armenian Center in Gdańsk.